All right, now we're going to work out the free responses. I forgot to say this in my mechanics video, so I'll say it here. My brand is World's Finest Physics, and if you're a student, you can get tutoring from me. If you want to get on my list for next year, you might be taking some difficult math or more physics. If you're a teacher and you would like to see some dynamic professional development, you can already see my presentation style. Head on over to Find Physics and see what our offerings are at the moment. Okay, see electricity and magnetism. This is going to be set one, and we're going to just go 1, 2, 1, 2, 1, 2. So what we've got here is we've got a electric potential, equipotential, isoline, contour map, relief map, whatever you want to call it. Non-conducting rod of uniform positive linear charge density is near a sphere. Right? We know the charge on the sphere. The rod and sphere are held at rest on the x-axis as shown above. The isolines, okay, so this is positive because we have higher potentials as we get to it. Negative because we're getting more and more negative potentials as we get closer to that. Okay, and positions A, B, C, D are labeled. Adjacent tick marks on the x-axis are 0.4 meters apart. Okay, it's worth knowing. Calculate the absolute value of the electric flux through the Gaussian surface whose cross-section is the negative 20 volt line. Okay, of course I have to move around in order to keep the lights on. Okay, so in other words, what is the electric flux through this Gaussian surface? Well, Gauss's law says integral E dot dA equals Q enclosed over epsilon naught. This is electric flux. That's what electric flux is. So that means this is electric flux, which means that this is going to be negative 2 times 10 to the negative 9 over epsilon naught 8.85 times 10 to the negative 12. And they said absolute value, so then that means forget your sign, okay? So then I'm going to say, why don't they just say magnitude? Why did they say, this is a physics exam, not a math exam. We say magnitude in physics, not absolute value. Okay, so it's going to be 225, basically 226. Newtons per coulomb times meters squared. Newton meters squared per coulomb. All right, that's the units right there, okay? If they ask you to calculate something, then it would be wise for you to put units on it, okay? A positive test charge, which is not shown, is placed and held at rest at position C. An external force applied to the test charge to move the test charge in the order C to E to D to A, and it's held at rest at each position, okay? So let's see, C to E to D to A. So let's trace this here. C to E to D to A. So we're going to go uphill to a higher potential, then the same, then uphill even more. Okay, so we're going to do energy bar charts. This is AP Physics C, electricity and magnetism. Aren't we a little too old for bar charts now? Okay, so let's see. All right, complete the following tasks on figure 2. Draw a bar to represent the relative absolute value of the work E to D, which is 0. The height of each bar should be proportional to the value of work C to E. If E to D or 0, write as 0 in the, so this is 0. Why is this work 0? Because you moved from the same voltage to the same voltage. Now, let's look here. We're going from negative 20 to 0, and then 0 to, is that positive 30? Yeah, okay. So then this is going to look like this, because this is basically 10, 20, 30. Okay. Draw a bar to represent the relative absolute value of work drawn by external. Hey, calculate. Oh, okay. Well, then that's fine. All right. Calculate the approximate magnitude of the x component of the electric field at position B. All right. In case you're wondering what I did, I just did work as Q delta V, and the delta V here was negative 20 to 0. Then this was 0 to 0. Then this is 0 to 30. Okay, does that kind of make sense where I came up with these amounts of work? All right, volts, 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 volts. X electric field at position B. At position B, what we have is we have 20 volts, and I'm going to say maybe 0 volts. But how far apart are these? I don't know. Okay. So one of these tick marks is like 0.8. So then this looks like maybe 1.4. So what is 1.4 times 0.4? Wait a minute. All right. So, okay. So, yeah. So 0.8. All right. So 0.8 and 0.4. Okay. So each tick mark, each millimeter is 5 centimeters. Each millimeter is 5 centimeters. Okay. This is why you bring a straight edge with you in the AP physics exams, you morons. Okay. So we got 14 millimeters. So it's going to be 14 millimeters times 0.05 meters. That's 0.7. That's believable to me. Okay, so now I'm going to say E is delta V over delta X. The delta X is, what did I say it was? 0.7. That's the delta X between, what were those two voltages again? 0 and 20, right? Between 20 volts and 0 volts. And then this would be 20 minus 0. So whatever 20 divided by 0.7 volts per meter is. So 20 divided by 0.7 is 28.57 volts per meter. Okay, well, whatever. All right, a positive test charge is now placed at position D. The test charge released from rest. Indicate the direction, not components of the net electric force exerted on the test charge immediately after at position D. All right, so at position D, which is here, we're going to put a positive right here. So we're going to put a positive right here. Then the initial direction of the motion is going to be perpendicular and toward a lower potential, which is going to be up. All right, so in the positive y direction. Without using equations, just phi. Okay, well, the electric force has the same direction as electric field. Electric field is perpendicular to the isoline and points toward lower potentials, which is up. Okay. Oh, of course. Why would it not be this way? Okay, the sphere and the test charge are removed. The rod has length 4L. Uniform charge density lambda. The rod is held at rest on the x-axis in the orientation shown. Position P, which is not shown, is some distance xp from the origin. All right, well then why don't I P? xp. Okay. The electric potential, using integral calculus, derive the expression provided. Okay, so you have to say this. You have to say V is integral. I meant the K, Q over R. So the dV of one single piece is K dQ over R. So V is the integral of K dQ over R. And then you're going to say, okay, lambda is dQ dx. So that means dQ is lambda dx. So then we're going to say V is integral K lambda dx over R. R is the distance from one of the pieces to the point of interest. This is X, the location of one piece. This is R. So R is XP minus X. Okay. So this is going to be XP minus X. Okay. And then we're going to integrate this from 0 to 4L to go from the right to the left to the right side of the rod. Okay, here we go. The K lambda is going to come out. It's all constant. And I get integral 0 to 4L of dx over xp, a constant, minus x, a variable. If u is xp minus x, du is negative dx. So I need a negative here and a negative here in order for this to be du over u. The integral of du over u is natural log. So I'm going to have natural log of xp minus x at 0 and 4L. So then I'm going to get negative k lambda natural log of xp minus 4L minus natural log of just xp. And now I'm going to distribute the negative. And then the property of logarithm says he's on top and he's on the bottom. So k lambda, natural log. This one is positive, he's on top. And this one's negative, he's on the bottom, which is exactly what that is. All right. Oh my gosh, is it ever going to stop? On figure 4, sketch a graph of the x component of the electric field from the rod as a function of x in the region 4L to L. In other words, I guess this is shaded because they don't want you to draw in that region, okay? Okay, so, hey, I have a calculator. Oh, of the electric field. Well, why would the electric field just decrease? Why wouldn't the electric field just decrease? I feel like the electric field would just decrease kind of the same way that Coulomb's law would. There's like some, is there a value right there? I'm not sure. I think it would look like that. Okay, I think it would look like that. So here's what I'm going to do. What I'm going to do is I'm going to just make up numbers for these things. So let's just do natural log of x over x minus 4. And we're going to set the table decimal. Shut up. And we're going to go times 2. Okay. Oh, and then maybe, I guess I can't do, oh, never mind. Okay, let's just do that. Okay, so you notice it's not even defined yet. And does that go to infinity? I think that goes to infinity. I think that electric potential might go to infinity because natural log does that, you know? Yeah. So so then this is actually going to have an asymptote also. This is not going to be an actual value. This is going to be an asymptote. So there's an asymptote. Why did you say that, Frensley? Because the electric field is the slope of electric potential. And if natural log reaches a vertical asymptote, that's an infinite slope. And if the electric field is the slope of electric potential, this is an infinite electric field. Okay, now we're going to do the other one. Oh, way to go, guys. This is really a different problem, isn't it? All right. Hey, we didn't make another problem. 90 degrees. Good job, College Board. Why even make 2 sets? Calculate the absolute value of the electric flux through the Gaussian surface. Oh, it's this again, okay? Whose cross-section is the 0. Okay, so once again, it's just going to be Q enclosed over epsilon naught. The Q is 1 times 10 to the negative 9 over epsilon naught, which is so basically it's going to be half of what I got before, and half of what I got before would be 113. Okay, so 113 Newton meters squared per Coulomb. Okay, now let's see. Okay, it's this task again. Why even have 2 sets? C to E to D to A. Okay, let's trace the path of this mofo. Okay, C to D to E. Where's A? Oh, and then to A. Okay, so C to D is negative 20 to 0, then 0, then 0 to negative 10. Okay, so this is negative 20 to 0, volts, 0 to 0, volts, and then 0 to negative 10 volts, but it says absolute value of the work. So then that means that this is 0, and this is going to be, did I read this wrong? C is negative 20, D and E are 0 to A. Okay, am I going to just split here? Is this what you wanted? Whatever. I hope you have fun reading this. Okay, calculate the approximate magnitude of the exponent of the electric field position B. Oh, look at this. Man, we're really doing it different now. B is on this axis rather than the other one. Okay, well, let's have a look here. All right, so what is this still the same scale that we had before? Let's have a look here. Okay, so yeah, it looks like 8 ticks to 0.4 meters. This is 30 ticks. So 30 over 8 times 0.4. Okay, so this is 1.5. That's believable to me. Okay, so the delta X, this delta X is 1.5 meters. The delta volts is 10 volts. So it's 10 over 1.5, which is 6.6 repeating. Okay, E equals delta V. It's easy to go through all these problems when they're basically the same. 10 volts over 1.5 meters, 6.66666 volts per meter. Okay. All right. A positive test charge is located at position C. Let's look here. Where's C? The positive is right here. And this is lower potential. Oh, so he's going to want to go straight down because that's lower potential, the negative Y direction. And then it's going to be the exact same justification as before. So if you're looking at, if you skip past question 1 of set 1, then just go back and see my explanation on that. Okay, the electric potential is that. Derive this. Okay, I guess I'm going to do it. YP. So if this is YP, we're going to split this into little pieces. If this piece has height Y, then the R to that piece is YP minus Y. Okay, so V integral K dQ over R, integral K lambda dy really over R, which is YP minus Y. Okay, so this is basically the same thing we did before, but just vertical, right? Okay, and so that's going to be K lambda, and we're going to go from 0 to 2L, 0 to 2L, dy over yp minus y. So if u equals yp minus y, du, yp is a constant, equals negative dy. So negative and a negative. So negative k lambda, this is going to become natural log of yp minus y from 0 to 2L. So then I'm going to say negative k lambda, natural log yp minus 2L, minus natural log of just yp because you plug in 0, okay? And then I'm going to distribute the negative, and then k lambda is going to be natural log as a single natural log yp over yp minus 2L. Okay, do you see that? All right, okay. And again, the electric field is going to be the exact same story. It's going to have this asymptote, and it's going to become less and less as you get farther away. All right. Oh my gosh, it's 2 resistors in series. Oh, it's 2 resistors in parallel. What am I going to do? What 2 totally different problems? Oh my gosh. Okay, the students are asked to determine the resistance R of 2 identical resistors. Screw you. 1/2 R. Let's just get that out of the way right now. Okay, the resistors are in parallel with each other. They're basically a single resistor is worth 1/2 R. Students have access to the voltmeter, potential difference function of time. The students are required to measure a quantity that decreases with time. Okay, so the voltage on the resistors. Okay, to determine R. On the circuit diagram shown in Figure 1, draw the voltmeter using the following symbol. The potential is that decreases. Okay, fella. All right. Let's see. Describe a procedure for collecting data that would allow students to graphically determine an experimental value for R using a decrease over time. Okay. Close the switch at time equals 0 for the voltmeter. It did say the voltmeter that would measure as a function of time. Okay, right? Close the switch, time equals 0. Measure values of the voltage of the resistor. It's like this is a lab I do with my students. As a function of time. And then what you actually do is you graph the natural log of the volts versus time to get a line whose slope. Oh, so we want R. Do we know the value of L? We know the inductance. Okay. Can be used to find R. Okay. All right. On the axes in Figure 2, produce a graph that represents the expected trend of the data by completing the following time. Label the quantities graphed on the vertical horizontal natural log V, T. Sketch a line or curve. Sure will. Label any appropriate intercepts and or asymptotes in terms of the quantities provided. Okay, well, this is going to be the natural log of of the EMF, actually. That's going to be the natural log of the EMF, okay? All right. And then how would we find the experimental value of the resistance? So basically what you have to know is you have to know that the voltage on the resistor as a function of time is equal to the battery's voltage. Wait a minute, this is wrong. The voltage on the inductor is what decreases. No, I'm thinking about this like it's a capacitor. The voltmeter is supposed to be right there. So the voltmeter is supposed to be right there. This is still technically correct, though. Okay. Yeah, the voltage on an inductor decreases with time because the inductor acts like an open switch, then acts like a closed switch. Man, I'm screwing this up. Okay, so I need a nice stiff drink here. All right, wet my whistle in order to stop making these mistakes. Okay, so all right, the voltage on the inductor is going to exponentially decay. I happen to know what this looks like. I mean, they didn't make you derive it using calculus. And by the way, this is the equivalent resistance, which is 1/2 R, right? So I'm going to say this, say the natural log of V is equal to the natural log of EMF plus a negative R over 2L times T. So slope of the above graph is negative R over 2L. So R equals negative 2L times the slope, which is also negative. And then that's how I would get it. All right. Starting with an appropriate application of Kirchhoff's loop rule, derive but do not solve a differential equation can be used to determine the current I in the inductor as a function of time t. Okay, so in the circuit, you've got a battery. You also have a resistor, and you have an inductor. So you're going to have a voltage up for the battery, a voltage down for the resistor, and that is the down voltage for the inductor. And that's it. That's a differential equation right there. Okay, after maybe if I'm going to derive, maybe I'll say battery voltage minus resistor voltage minus inductor voltage equals 0. Like when it says derive, you have to show steps, right? I just wrote it. But I said it as I wrote it, but you can't talk during the actual exam, so I guess I'm going to communicate that up there. After reaching steady state, the absolute value of the potential difference across the inductor is 0. The students replace the original inductor with a new inductor that has its own resistance. The experiment is repeated after a long time. The absolute value of the potential difference across the new inductor will be something. Something's greater than 0. Justify your answer. In case 1, the inductor in steady state has 0 voltage drop. Why? Because steady state means I is constant, di dt is 0. The voltage on the inductor, which is L di dt, is 0. Right? Okay. But if the inductor has its own resistance, then the voltage on the inductor will be IR plus L di dt. This is still 0, but this is something. So you'll have a voltage equal to the I times R ohmic voltage drop on a resistor. Oh, it's magnetism. Hey, is this going to be the same thing? It's known inductance. I'm just going to go really fast for this because it's the same thing. Oh, I've got to measure a quantity that increases with time. I don't want to. Okay, the quantity that increases with time. Now I need to put the voltmeter across my 2 R's because they're identical resistors, okay? And then the procedure, same procedure as before. We're going to, the voltage is going to increase. I'm just making sure I'm not crazy this time, okay? All right. Now, this time, though, you can't really take the natural log. That's not going to help. So I'm thinking about what I'm going to do. I still want to take voltage as a function. So I still want to take voltage as a function of time as after the switch closes. I mean, that's what I want to do. So then here's what's going to happen. The voltage as a function of time is going to look like this, where this is the EMF. Okay? And then what I'm going to say is I'm going to say the voltage on the resistors is EMF 1 minus e to the minus RT over L. It's actually 2R because that's the equivalent resistance. So here's honestly maybe what I would do is, well, maybe you're allowed to say that you can fit a curve to this. I'm going to fit y equals A, 1 minus e to the minus bx to this, and then set b equal to 2 r over L, solve for r. Is that something you're allowed to do? I think you can do that in like Desmos and stuff, right? In Desmos, because Desmos can do just about everything. I think that Desmos could die on the cross for your sins. Okay, it can do just about everything. Now, what else do I want to say here? Another thing I might think is I might say, okay, well, what is dV dt? That would be EMF 0 plus 2 R over L, e to the negative 2R T over L. And then I might say this. I might say get the dV dt right at time equals 0. And so at time equals 0, this will be 1. And then so dV dt will be equal to 2R EMF over L. And then solve for R, assuming we know L and the EMF, which I think we do. Derive but do not solve a differential equation. It's the same one again. EMF. So wait a minute. Let me derive it. The via the battery minus the via the resistor minus the via the inductor is equal to 0. The EMF minus I times R is a 2R. Shit. Did I forget to put that on the other one? Half. Okay, I times 2R, L di dt equals 0. That's a differential equation. Okay, the absolute value of the potential difference across RA is that, which is something. The new inductor has non-negative resistance, so RA is going to have less voltage. Okay, so before RA was equal to half the EMF, RB had the other half because the inductor has no voltage drop in the steady state. Right, I said this on the previous set, right? Okay. Now the inductor has some V equals IR voltage drop. So RA and RB are splitting a voltage drop less than the EMF. So it's going to be less. Okay. Last one. Let's do some magnetism. You got it. It's like, oh, it's like an American flag. Oh, beautiful for space. Okay. What's going on here? A wire is connected to a resistor of resistance R. A rigid rectangular loop of width L and height 2L. An external force is exerted on the loop so that the loop always moves with a constant speed in the positive X direction. Okay. The loop then enters region 1. You don't need an external force until you enter the region, so whatever. Of the external uniform magnetic field of magnitude B that is directed in the positive Z direction. Region 1 has boundaries. Oh, gosh, I don't even want to read this anymore. Enters region 2 with 2 external uniform magnetic fields, each magnitude B, that are parallel but are directed in opposite directions. Region 2 has that. Okay. Point S is the midpoint of the leading edge of the loop and is aligned with the horizontal boundary region 2. Okay. Let's keep going. Sketch a graph of the magnetic flux through the rectangular loop as a function of its position of point S. Okay, so once point S gets to here, we are going to begin the process of taking into the page magnetic field. What is their decision? What are they deciding here? The positive Z direction indicated corresponds to positive phi. All right, so then this is negative. So we're going to take in more and more negative flux as we travel from L to 2L. So as we travel from L to 2L, we're going to take in some positive flux. I'm going to use a double size here. Okay, so now at 2L, we are now completely in the field. We're going to travel another half with nothing interesting happening. The L stays, the flux stays the same. That brings us to here. There's point S. And then now what's going to happen is that we are going to take away negative flux and at the same time add positive flux. So as we go from 2.5 to 3.5, the flux is actually going to go to zero. This is zero flux right here. So we are going to linearly go back to zero flux, and then it actually stays zero for the rest of the time. Now, why is that? Because this is equal positive negative, this is equal positive negative, equal positive negative, so it's just zero for the rest of the time. That made my brain hurt. Okay. That's the end of school. Consider the instant when point S reaches 1.5 L. U. Indicate whether the current that is induced in the rectangular loop is clockwise. Oh, gosh. Okay. So when we're at 1.5, we're moving into the field with an increasing flux. I teach my students that for an increasing flux, they use their left hand because that is the negative of Lenz's law. A decreasing flux, you use your right hand. You put your thumb in the direction of the magnetic field and you curl your fingers, and the current induced will be a counterclockwise current, okay? It's a counterclockwise current, okay? Just my answer. So, since the flux into the page is increasing, I put the thumb of my left hand into the page and my fingers curl counterclockwise. Okay, let me sum it up for you. Left hand, since flux increases, thumb into page because magnetic field is into the page, and the fingers curl in the direction of the induced current. Yeah, let me just tell you, when you have to explain the right-hand rule to the reader, you have to basically treat them like they're completely moronic, okay? You have to basically spell it out to them like you would to like a third grader, all right? In order to get all the points. Derive an expression for IR when point S reaches at, if IR is 0, no, it's not. So I'm going to say this. I'm going to say EMF is d flux d time, and it's equal to I times the R. Okay, do we have an R in this circuit? Yes, we do. Okay, so what is this? Do I have to? I did not have to label this, but this, well, how much flux is that? That would be what? 2L squared times, is there a value of B given? Yeah. Okay, so this would be 2L squared times B. That's 2L squared times B. So then what is this? This is, oh, this is not even d flux d time, okay? So never mind. How about this? How about EMF is d flux d time dx dt equals IR. Chain rule, bitches. All right, IR. And then what is delta flux over delta time? That's going to be L, 2L squared B. So it's going to be 2L squared B is the rise. The run is L, making 2LBV, velocity equals IR. So then the I would be 2BLV. I've always written in that order over R. Okay, derive an expression for the power dissipated in the resistor when point S. Okay, great. Power equals I squared R. So then that's going to be 4B squared L squared V squared over R squared times R. Cancel one of the R's. Okay, I think everything I did is good. Oh my gosh, it's 2 more pages. Oh, what? Oh my gosh. Okay, we're making it even bigger. Okay. Total energy dissipated by the resistor in the rectangular loop as point S moves from 0 to the is E, the original amount. The vertical boundary between regions 1 and 2 is now shifted to 1.5 L. After the boundary is shifted, the rectangular loop again moves the speed V in that direction. The total energy dissipated is E nu. How do they compare? Oh, if I know. Okay, so as this moves into this region, here's what's going to happen. We're going to gain magnetic flux, and then we're not going to gain it anymore after that, and then we're going to lose it. So here's what the graph of flux versus X is going to look like. It's going to look like this. Okay, yeah, it's going to be 0 flux. Then you're going to gain that. I'm going to make it positive. Okay, sue me. You're going to gain flux until S gets to here. Then you're not going to gain any more flux anymore. And then once S gets to here, you're going to start losing this flux because these fluxes add to 0. So then it's going to go back down to 0, and then it's going to be 0 for the rest of the time. So I'm going to say the new energy is less than the original energy, and I'm going to say why. The reason why is I'm going to say the current is induced for less time. The current is induced for less time. And I even think I should say that the induced current is less. And the maximum induced current is less. The maximum amount of the induced current. No, I think the induced current has the same maximum value. I'm sorry, I take that back. Okay, the current is induced for less time. So it's actually going to be like the same shape here, except now it's going to flatten out forever, right? So it's going to flatten out forever. So you get the same current, but for less time, okay? So you're going to get the same current, but for less time. Okay, so your current is induced for less time. So same power while the current is induced, but less time. Energy equals power times time, less energy. All right, the original magnetic fields are modified so that the region contains just a uniform magnetic field in the negative Z direction. A new wire is connected to the resistor, resistance R, form a rigid triangular loop. Okay, again, it's always going to go the same speed. There's the lower corner right there. Sketch a graph of the induced current IT, and the triangular loop as point S moves. Okay, so here's S. Here's the rest of the triangle. Now here, when S is here, here's going to be the rest of the triangle. And the area is going to be only 1/4. So, like 1/4. And then when you reach 2L, it's going to be the full triangle. So that's going to be 4 of these. 1, 2, 3. So it's going to be kind of like a parabola. And it's going to flatten out because there's going to be nothing more taken in. All right. Stop the light turning off. Okay, so here we go. Now we're going to do set 2. Oh, What fresh hell is this? Okay, so a wire is connected to this resistance R, square loop of side length D. External force keeps the speed going. The loop enters region 1 of external uniform magnetic field of magnitude B in the negative positive Z direction. Good. Region 1 has boundaries and 2D, and the loop later enters region 2 of twice the magnetic field. Okay. I'm going to use green here. On the following axes, sketch a graph of the magnetic flux phi through the square loop as a function of the point. Okay. All right. So here we go. No flux, no flux, no flux, but we're about to start having flux. Okay. Now, this is going to be an amount of flux here. 0, 0, 0. This will be 1/2 d squared times b, because it's half the area, d squared, in a magnetic field B. And then now this is going to be 1 full d squared times b. And then here, this is going to be 1/2 times 2 plus 1/2 times 1. My brain is so fried I can't even do basic fractions. 1/2 times 2 plus 1/2 times 1 is 1.5. Okay. So then this is going to be 1.5 d squared b. Then this is going to be 2b times d squared. So that means that this is just a line. That's just a line. That I could have swore this was going to be a piecewise. I was fully expecting a piecewise. It's not a piecewise. Okay, and then it's going to be flat. Then it's going to be flat. And then as we get to 4.5D, it sinks back to 0 again. And it's positive because out of the page is positive. I was fully expecting a piecewise graph there. I mean, it is piecewise, but I meant the piece changing at D, but it doesn't. That is so effed up. Consider the instant when point S reaches that. Okay, so the same thing I'm going to do this time at 1.5, which is, let me maybe do it in highlighter. All right, at 1.5D, which is right now, the out of the page flux is increasing. Left hand for out of the page flux is increasing, so it's going to be a clockwise. You saw how I did that before, and I feel like I want to quit doing this, so I'm not going to explain it again. Okay. Derive an expression for IS when it's at that. It's not going to be 0. Okay, so once again, EMF is two things, d flux, d time, and that's I times R. D flux, d time is really d flux, dx times dx dt, which is V. What is d flux, dx? Okay, what is this number? What is this? That is 2b times, or not to be, times d squared. So this is 2b times d squared. So now what I'm going to do is that d flux d time is going to be 2b d squared over 2d. Cancel, cancel, cancel. It's just b times d. Okay, so this is going to be b times d times velocity equals IR. So the I is b d v velocity over r. That's velocity v. Okay, I think that's allowed. Yep, those are all the letters I'm allowed to use. Physical constants, my foot. Okay, derive an expression for the power. Power, again, is I squared r. So that's going to be b squared, d squared, v squared over r squared times r. Cancels. All right. The total energy dissipated by the resistor in the square loop as point S is the original. The vertical boundary between regions 1 and 2 is now shifted to 2.5D. The square loop again moves the speed V in the positive X direction. Oh, Lord in heaven. Okay, so I need to do this. I'm going to do it with a pencil. Okay, so again, I'm going to kind of make a little sketch of the graph of flux versus time. So the flux versus time is going to be 0. And then the flux is going to increase here. The flux is going to increase here. Okay. As we go here. Okay. So from here to here, the flux increases linearly. Then from here to here, the flux is going to stay the same. And then from here to here, the flux is going to increase the same with the same slope. That's going to be the same slope. And then, thank you very much. And then the flux is going to decrease with the same slope that we already had. So here's what this is going to do. It's going to go from being this that I'm doing in blue. This is the correct answer. The new situation is going to be like red, like that. So you actually get the same currents for the same time. So this is going to result in the same currents for the same time. So I'm going to say the new is equal to the original. And this is because the same current values occur for the same lengths of time. Okay, so same current values give you the same power. The same length of time. Well, energy is power times time. So same power, same time is the same energy. Okay, sketch a graph. Was that what I was supposed to do? Sketch a graph the induced current? Oh, I did the flux. Okay, so this is the flux. So this is the flux. That's wrong. Okay, so the induced current is going to be the derivative of this because EMF is d flux d time equals IR. So I just need to do the derivative of this. Okay, so then the derivative will actually be this black thing. It's going to increase, then drop to 0 once you're fully in the field. Sorry, I got that wrong. Okay, so now this guy is going to do this. Okay, so I'm going to sketch what the flux is going to look like. So once we get to D, like this, the flux is still 0, but then look what's going to happen. What's going to happen is that the triangle is going to be 3/4 in and 1/4 out. So that means that this is going to be 1, 2, 3, 4, 3/4, and then now the triangle is fully in the field. So it's actually going to be a parabola like that, and then a constant flux. Do you see how that works, right? So the constant flux is 0 current, but this is a downward opening parabola. So you're actually going to have a current that goes like this or something like that, right? All right. So a bunch of teachers got back to me and said, yeah, my students said that this electricity and magnetism exam wasn't anything like anything they'd ever seen before. Yeah, I agree. Have a nice day.